Welcome to this demo as part of the multidisciplinary or cross-competence team in the innovation team. We develop this kind of systems. This is the one we want to show you today. We have in front of us a 5G SA private network system. So it's portable, has some wings, so we can put it in one place or another. It's based on 5G SA, so there's no 4G core, it's all full 5G. And from the RAN access perspective, we have millimeter wave frequencies that we use. Why are we using these? Because we are part of the TrialsNet project, TrialsNet consortium. It's a European project, research project, and it aims to make real use cases with large trials. We are part of the Madrid cluster. We are a few partners with ourselves, Telefónica, and UC1, University, Prosegur, and Yerba Buena. Okay. We plan to go next month to UC Center, where Prosegur will connect their devices, crowd monitoring, the radars, cameras, and robots to our 5G network. And also Yerba Buena will connect their cameras to our 5G. So why are we using millimeter wave? Give us a few advantages compared to the mid-band standalone that currently the operators use as a capacity layer. Okay? The main benefit is the bandwidth. Since we go to the to the high band, in this case 26 gigahertz, we have 800 megahertz available for bandwidth compared to the 100 that we have in mid-band in 3.5. Okay? So we can reach theoretical up to 4 gigabit per second in downlink and 400 megas in the uplink, compared to 1.5 gigas in downlink and 0.2 in the uplink. By tuning with certain features the TDD pattern, we could reach up to 1.8 gigas in the uplink compared to the 0.3 that we can get in the mid. The main other advantage is the latency. So in an equivalent system using midband, we can get up to around 15 milliseconds round-trip latency to Google, to public server. But if we use the millimeter, we put the latency down to 4 milliseconds. Okay. So what do we have in front of us today? We have the flat right here. First of all, we have the RAN access. Okay. So it's a commercial equipment from Ericsson. It's a router and a baseband using as a G-Node-B. Okay. Then we have the radio. It's an R5322, also commercial, available in the market. Okay, and one of the innovations we get here, especially from the RAS perspective, is the fixed wireless access feature for a high band standalone. That allows us to use only one radio and one baseband because we don't need the mid-band layer to use it as anchor. Okay? So in a commercial network, if we use millimeter wave, we need a mid-band layer. In this case, we don't need it. The great inconvenience of that is the device. There are no commercial devices in the market right now. So we are using a prototype provided by Qualcomm. Okay, and to that one we connect whatever we want to connect. So we can connect control centers, cameras, robots, and all the devices that we want to connect. Okay. Then the second innovative thing compared to the public network, let's say, is the local packet gateway. Okay, that has the user frame function. So part of the functionality, the user frame functionality that is typically located in a central core, in the 5G core, in the data center, we have bring it here in local. And then the thing that we don't see here is the 5G core in Tectonic in Leganés, where we have a transport network where we connect to it. Okay. Same schema, but with network topology. So this is the case of a regular 5G network where we have the UPF, the user plane function, in the local server in 5G core, in the central server. Sorry. So then the data, user plane data, has to go there and back. Okay. With this UPF in local, all the user plane traffic does not leave the private network. This gives us some benefits. especially in terms of latency, data does not go out, but also in terms of security and privacy of the data. Because we're talking about user plane data. The contour plane data in this solution, we still need to go to the central file. So, as a summary, what we get here, we have the great performance due to the millimeter wave, okay, both in throughput and latency, then UPF local, so we don't need to rely on a good transport network, and then the fixed wireless access for high band feature that allow us to have one baseband and one way. So let's see how this works in reality. We have a demo here. We have connected a mini PC, computer. We have connected it to the CPE. Okay. Then we have the air interface, the radio, and the G-Node B, and the rest of the net. First test here is when we have the speed test server located in our lab, Leganés. Okay. So let's see how it behaves. Here we have a certain throughput, but here the bottleneck is the transport network. We have shared it with the other demos, so we are limited by transport network here. Okay, so we're getting 400 megabits per second in downlink, for example, 8 milliseconds latency, which is not bad. Okay, so let's see in the other case, when we are using the local speed test server here, and our data does not leave the network. So we have around 4 milliseconds latency, and we can get the impressive speeds of 406 gigas in downlink, and uplink goes above 400 megas, you can see here. Another way to see this is even with a low or not so good transport network, we are able to get this important, impressive performance. So thanks for your attendance. Hope you have liked it.